Starting a new unit, Unit 3. It's all about optimization, or really, in other words, maximum and minimum values of functions. So everything in this unit has to do with that. Today is a bit of an oddball thing. Some of it is very similar to stuff we've already seen, and some of it is just kind of specific, but it gets us doing the kinds of things we're going to do for the rest of this unit and a lot of the rest of the course. Then tomorrow, which is the last day, happens to be the last day before March break, we're doing word problems. So it applies some of the concepts, but it obviously is going to look very different. There are several very specific kinds of word problems in this unit of this course. We're going to do a few of them tomorrow, and then we have the break. But the nice thing is, back on Monday, we're going to do another day of word problems, which will be good review after a long break, and look at some other types of word problems as well. Okay, so that's what we're doing. And then after that, the rest of the unit is essentially sketching, curve sketching. But it's all related. A lot of what we do throughout the whole thing is finding maximum and minimum values. All of the word problems are all maximizing something. In grade 10, you did questions like this: maximizing revenue, or finding the max height of a ball, or something like that. But we're going to do it using derivatives, not by finding the vertex of a parabola. At any rate, that's starting tomorrow. And then, like I say, there'll be curve sketching later on. So it's kind of broken up. This unit's kind of broken up into two separate sections, but that's how it looks. So everything's about maximum and minimums. Okay? And so today's algorithm that we're going to see in a few moments is a little bit like, I don't know, to me it's specific. It's a little bit odd, but it makes sense. It's pretty simple. Like today, in the grand scheme of this course, is pretty easy. It's not too hard to do, I don't think, and conceptually it's pretty straightforward. It's not complicated. It's kind of intuitive, but it gets us on that track of thinking about maximum and minimum values. Before we get to that, we want to talk about notation. I've used this notation a little bit in this course. Some people have seen it and some people haven't. After today, you are required to know it, because we will use the notation a fair bit throughout the rest of this course. So we would call this set notation. But the other type that we see is interval notation. Although actually, now that I think about it, I think the practice today doesn't have interval notation, but we will see it throughout the course, so I wanted to cover it. And some of you know this, like I said, and some of you don't. Again, your handout might have had mistakes on these, so make sure you fix them, otherwise you're going to confuse yourself. Interval notation is a little bit simpler, like it's a little bit less writing. It's not quite as many things. The other nice thing is some people forever get these signs wrong, and interval notation doesn't use those signs. It uses brackets, so I'm writing the equivalent of this in set notation, but using interval notation, right? A is less than or equal to x, which is less than or equal to b, would look like this: A to B. Comparing that to A is less than or equal to x is less than b, we know that it's pretty important if your interval or your domain or whatever includes the endpoint or not, or either endpoint at the beginning or the end. That can make a big difference. So in interval notation, that's how you show the difference. Square brackets are inclusive. Round brackets are exclusive. They do not include the endpoint. You can make a note. I think after we've done the examples, it will be clear, and you could just look and remind, oh yeah, right, that one goes with doesn't equal, right? Not equal to, because it's round. Like you can just compare all of the examples. But if you want to make yourself a little note, you can do that too. Square brackets, inclusive. Round brackets, exclusive. And we're just going to do some other examples of these ones. As you can see, it's a little bit less writing. It just uses brackets. Can't change the brackets. You don't use brace brackets, which are the squiggly ones. Those are usually used in set notation that we use for domain and range, that kind of thing. We use brace brackets. You have to use the square brackets and the round brackets for this. I guess one downside of interval notation is it can look like an ordered pair. So you would have to kind of indicate that you're talking about an interval, not just randomly write something, don't write this down, but 5, 10. Is that the ordered pair? X is 5, Y is 10, or is that an interval from 5 to 10? Right? So that could be a little bit unclear. So now if I'm not including A, but I am including B, it would obviously look like that. And this is the one that I was just referring to. If I'm not including either, kind of looks like an ordered pair. You always start with the smallest one, so A will always be less than B in these cases. If you did it backwards, you're in luck. Your reader would understand. It would just go, well, that's weird. Why did they start with the bigger number? That doesn't make that, like, that's just a bizarre way of looking at it once you get used to this stuff. Again, don't write this down, but the nice thing is you can't really make a mistake. Some people sometimes do this. So you always start with the smaller one. But this one isn't just wrong in terms of conventions. This makes no sense. 4 is not less than 2. There are no values of X that would make this work. Unless that's what you mean, but you would never do that, right? This doesn't make any sense. 4 cannot be less than 2. This is what I was talking about if you've never learned how these signs work. If you did it like this, well, sort of that's okay, I guess, but it's still not really, conventionally speaking, correct because we always start with the smaller one, so it just looks weird to us. And same thing here, you always start with the smaller one. How do I show an interval that's only has one end point, otherwise goes up forever? So this one has a minimum value of A. X is greater than or equal to A, so it's got a minimum of A. It includes A, so I show inclusive. And then we use infinity. And infinity will always have a round bracket because you can't reach infinity. It's not a thing. It's not a number that you can get to. And if it's X is less than B, I go to negative infinity up to B, and I don't include it. So that's how you would indicate these two types of intervals that only have one end point. So just some notation, just to be aware of it. If we're not using it much today, and then all of a sudden it pops up later, you can look at it, come back and look at it on your handout and make sure that you get it. Okay, now let's actually talk about what we're talking about today, the maximum. This is the part that we kind of already know, but we're going to formalize this a little bit more and really, like I said, really start to use it a lot. So the maximum value, the maximum function value, the value of a function means the y. So whenever we're talking about the function value, we're talking about the y at some particular x. X is how we locate where it is, but y is the value that it is. I hope that makes sense. So we're talking about y values here. The y value, the maximum value of a function, and for the most part, it doesn't have to. I think all the questions we look at today will, but we're talking about continuous functions. These functions at least are continuous on the interval that we're talking about. What if it wasn't continuous? Well, there's a few problems. What kinds of things aren't continuous? If it has a break, like a jump, that would be tricky because we'd have to somehow figure out what the left-hand limit is and what the right-hand limit is, and this process wouldn't really work for something like that. After we've done a few examples, you can go back and think about that and be like, okay, yeah, I don't know how you would figure out what the minimum value is if it's got a break in it. If it's got an asymptote, a vertical asymptote, what would the maximum value be? I mean, it wouldn't have one because it goes off to infinity. Or minimum value, it goes off to negative infinity, right? So typically speaking, those won't really come up much today. It is, if there was an asymptote, you would have to take it into consideration. You would say there is no maximum value because there's a vertical asymptote that goes off to positive infinity. Like, I guess that's how you would say that. But for the most part, the problems that we're looking at, that won't be relevant. When we do curve sketching, it absolutely will. Okay. So what does that mean? It means the derivative exists, or the derivative, sorry, doesn't exist, but has a derivative at all points on a continuous interval. The maximum value will occur at a peak, right? Or a cusp. We'll look at that in a moment. A cusp is kind of like a peak, but it's a little bit different. I need the handout. Okay. Yeah, just up there. And the minimum value can occur at a trough. Okay, so what is a peak? What is a trough? Imagine you have some kind of function that is coming along like this, but it hits the beginning of our interval, which we just kind of said was a over here, right? And so continues up, but peaks, and then troughs, and then hits there. And maybe it goes down again. I don't know what it does, but something. So obviously there's my max. That's the maximum value in this interval. Like literally just looking at the picture, that's the highest point this function reaches on this interval. Maybe the function doesn't curve and it continues to go up. The function itself overall may get bigger. Maybe it goes off to infinity. We only care about this particular interval. And this is obviously the minimum in this interval. And then there's the end of our interval, which is some given value b. The interval is always given. What do we know about the derivative? We don't know what this function is. That's not the point. We're just illustrating, visualizing right now. What do we know about the derivative at those two values? It equals 0. So that's really, really important. At both these places, the derivative is 0. So in a defined interval, the maximum or minimum might occur where the derivative is equal to 0. Don't you agree with that? Based on that little description. Okay, where else might the maximum or minimum values occur? Again, if this is A and this is B, maybe it starts way up here, goes down, and again continues off in both areas. So I've got peaks and troughs, but they're not the maximum or minimum values in this case. So this is a peak, and this is a trough, but this is my max, and this is my min. So in a given interval, the maximum or minimum might occur at the end points of the interval, at A and at B. This might be like, okay, so what? Like, where are we going with this? It'll be obvious pretty soon. Any questions so far? See what I mean? It's pretty, like, doesn't really get more complicated than this. Hard part is always accurately getting the derivative, right? That's going to be your harder part. Last example, A and B, is what if it's something like this? So these are cusps. They turn at a point. They don't have a smooth turn like a peak or a trough. And this is obviously my max. And this is obviously my min. Again, cusps might be maximum and minimums, or they might not. The minimum you might have a cusp, but the minimum is an endpoint, like, right? What do you think is true of the derivative at those points, or who remembers we have actually talked about this a little bit before? What would be true of a derivative? Very good. So in these cases, y prime does not exist at cusps. So in conclusion, from these three diagrams, if we want to find the maximum or minimum intervals on the maximum or minimum values of a function on a given interval, we got to check where the derivative is 0, where the derivative does not exist, and the two endpoints of the interval. We check those values and literally just look at them and see which one's biggest and which one's smallest. So we kind of overcomplicate it by calling it the extreme values algorithm. or the algorithm for maximum and minimum values. Extreme values, or extremum, is another way of saying maximum and minimum. When you have a turning point, we call it, if you have a turning point like this, okay, I'll draw it as well. If you have a turning point like this, that's called a local maximum. We're not going to use this terminology much today, I don't think, and this is a local minimum, because the function may have an overall minimum. It might turn and go back down and go lower, right? But locally, as in if I define some interval around there, like I could just do this, that's the lowest point there. It's a turning point, right? And that occurs when the derivative is 0, when you have a horizontal tangent line. Heads up, there's one other, I shouldn't say one, but one other common place that we see horizontal tangent lines where the derivative is 0 is not a local max or min. It's like a cubic twist. A cubic twist has a horizontal tangent. The derivative is equal to 0. So just because the derivative is 0 doesn't necessarily mean you got a local max or a local min. We'll talk a lot more about this when we sketch. So we do some checking and testing to see what's going on, to see if it's a local max or min. But for today, we're just literally going to check the values. So here's the algorithm to find the maximum and minimum function values, in other words, y values, of y equals f of x on the interval from a to b. It pretty much always includes a and b for this process because, like I said, I don't know how you would do it if it was like up to b but not including b. I don't know how you would do it. First step, find all x values where f prime is 0 or f prime does not exist. And so to do that, you have to take the derivative. So you're given a function, you take the derivative, you determine where it's 0, where it does not exist. We've already done that in the last unit. That's why we did that on that day. Okay. Then you find the function value or values, the y value, for each of those x values in step 1. So you're going to have a list of y's. Then you find the function value for each endpoint, f at a and f at b. Notice again that this is all in f, not in the derivative. In this process, we're not plugging into the derivative. We're plugging in these x values to the original function. That's the one that we care about. The derivative is just telling us something about it. Then you got a whole list of y values, and you literally just look at it, and you're like, that one's biggest, that one's smallest, now I'm done. You write it out. This question wants us to illustrate with a sketch, but that's it. So yes, we have this sort of extreme values algorithm. It's got this funny name, and step 1, step 2, step 3, but it's intuitive. It's not a bad idea to still think about it as step 1, step 2, step 3, just to make sure you hit all your points and your solution is properly organized, because that is part of what we will be looking at. But it's a pretty intuitive process, I think. Does that make sense? Okay, let's try one. Let me know if you have any questions. Question says, find the maximum and minimum value of each function on the given interval using the extreme values algorithm for maximum and minimum values. Illustrate your results with a sketch of the function in the given interval. The sketch might be one of the most important details of today because you need to start putting together the details of what you're looking at and how it defines the function and how you can visualize the function for later on when we start sketching. And you'll ask questions today like, how do you know it does that? How do you know it did that? How do you know it turns there? How do you know it looks like that? But after today, that's what you want to be able to do. And it, just like curve sketching in MHF, you're getting all these details, properties written out, and then you're putting them all together to figure out what it looks like. We don't know exactly what it looks like, but generally we do. First one, super easy. Our first step is to find where the derivative is 0, it does not exist. So first of all, we need the derivative. And if you need my help taking this derivative, oh boy, you're in trouble. And in some cases, after you've taken the derivative like this, you're going to do the full simplification, like you might do that here. In this case, because it's polynomial, I'm just choosing not to, but you could. But after you're done with the derivative and you got it kind of in the completed form that you want it in, so I want you to show this, f at x equals 0. How do I figure out where that's equal to 0? Is that something we've learned how to do? Yeah, we just set it equal to 0 and factor it, solve it like in grade 10. Don't get stuck on that like, ooh, I forget what to do. Oh my gosh, no, we know how to do this, yeah. Yes, thank you. So I'm going to common factor out of 3. So 4 and negative 2. And we are going to be a little bit particular, at least. This isn't a fully formal process, but about how you organize your solution so that it's clear that this is you determining where the derivative is equal to 0. And then over here, where does the derivative does not exist? Does anybody want to add some value to this here? How are we going to figure that out? Yeah, this is a polynomial. We know like the function's a polynomial, but so is a derivative. And we know all polynomials exist everywhere. So f prime exists for all x. And you've got to make that statement. If it doesn't exist somewhere, we're going to say, and we'll see that later, obviously. We'll say that it doesn't exist. If it exists everywhere, you have to state it exists everywhere.
Can I write x here?
Yep, no, you can write x here. That's fine. Okay, so that was step 1. I wouldn't usually number the steps, but if it helps for our first example, you might want to, I don't know. That was step 1. Step 2 is take the values that we found in step 1, sub them into the original function to find those y values. But before we do that, does anybody have anything they want to? So that's always something you want to think of. If you went and found f at 4, A, you're going to mess yourself up. But B, it would also be like you're wasting your time. It's not in our interval. So I'm going to make a note of that, right? Not in interval. We still show it as a solution. You don't just ignore it from the beginning. Show it as a solution. Give it a little circle. State that it's not in the interval. And now we don't have to worry about it anymore. Okay, so step 2. In this case, is pretty easy. I'm just finding f at negative 2. And it's f, not f prime, which is 38. And that's it. There was only that one value because there are no places where the derivative does not exist. And it turns out there's only one where it's equal to 0. That's in our interval. So now step 3 is also find the endpoints of the function, which in this case are negative 5 and 3. And they work out to be negative 70 and negative 62. You can check my math on that if you want. If you had a bunch of those to check, doing that little trick where you program the function into your calculator and then just quickly punch the values in might be a useful, efficient use of your time. If you don't know what I mean, you can ask me about it after. I'm not going to go over it right now, but we did this in MHF, right? And so if you have a calculator like that you can program functions into, save you a bit of time. Then you would have, then you would say you have two maximums, like they'd be equal, you mean? Yeah. Then you would just say that. It won't happen in this. Do you know how to take the derivative of a sine? No. No one does. No, just kidding. That's not true. We have a whole unit on trigonometry, but not yet. Okay? It's next, though, I think. All right, so we're not quite done. We've done all the work, but now we have to make our final statement, and in this case, it asked us to do a sketch as well. So we say, therefore, the maximum is, well, what is it? 38? And we're going to say when it occurs as well. Some of the questions sometimes say that. On the test, it probably will. I don't think the homework does, but I'm going to tell you to add that in. So the max is 38 when x equals -2, and the min is -70 when x equals -5. Any questions? Your final statement should always look like that. Our sketch is going to be a little bit different from what we've done in the past. We're not even drawing x and y axes. Sometimes the x and y axes won't kind of be on there, or they wouldn't be worth trying to draw. We don't really have a scale, although we are going to sort of think about what the function would look like sort of a really rough scale drawing, I guess you might say. So this is -5. I'm going to mark, whoops. I am going to label it. So this is -5. That was one of my intervals. The other side was 3. The minimum is -70 when x is -5. So I'm going to start down here. And that is, and I'm going to label it, -70. The max is 38 when x is -2. So I'm going to keep that a little bit closer to -5 because it would be a bit closer to -5 than it would be to 3. And then what happens, it comes back down because at 3, I'm back at -62. So I can't go as low as -70, but I'm going to go, and that was maybe, I want to go a bit higher even just to be careful. So there's -62. And you don't have to do this, but you might. We know there's going to be another turning point or something happening at, we actually do know that it's a turning point if you think about the degree of the function, but at x equals 4. So you don't need to include this, right? But just because this is what we're going to be talking about, I do know that at 4, which is just after 3, something else would be going on there. This was the maximum value of 38, and that happened at -2, 38. Do I know if anything interesting is happening in here? Well, I kind of do, because if it even did that, I would have derivative equal to 0 there. Like there would be something in the derivative showing me. Do I know that it doesn't go like this? Yes, because that would be turning points which would appear in the derivative. Also, the degree of the original function wouldn't allow you to have that many turning points. Okay, so we do kind of have a sense that that's what that function looks like in that interval. Any questions? All that labeling is required. Okay, but notice that I don't have an x-axis. I don't even have a y-axis. I don't have 0 marked anywhere. Like I've only marked the important points, but that's the way we want to see it. So don't miss any of those labels. Some of the derivatives that we did in the last unit will be like the hardest ones that you're going to do that are in this kind of a form, okay? Those ones that have like exponents of 4, 5, and 6, we don't really sketch things like that, okay? So now we do all those hard ones to push our abilities so that we can hopefully be extra good at the moderately easier ones that will pop up throughout the course. There are some other functions that are hard to take the derivative of that will come like in trig and that kind of thing later on. So I'm not saying there won't be hard ones down the road, But when we're sketching, we're not going to see any of those crazy ones. Okay? This would be a very good example of something you might sketch. So derivative's a bit easier. And now you can go ahead and give it a try if you want. Again, make a note of your interval. We're going to watch for that if any of the values lie outside. That's such an easy step to miss and forget about it. And then A, you're going to get the wrong answer, but also you're going to be doing extra work, right? And this is where, like, you know, if you're doing a big curve sketch and you get the first derivative wrong, yikes. Who knows what's going to happen next? You're going to have like x-intercepts and y-intercepts and turning points that don't match or asymptotes that don't match. Like, you're not going to be able to draw it if you get the derivative wrong. So you got to be careful. You got to be good at this. You got to know how to simplify this fully so that you can figure out where it's 0 and where it does not exist. You could common factor out an x. In this case, I don't think that's going to be helpful. I think the better way is to expand and simplify on top. I get 8x cubed plus 8x from there, and then I get minus 8x cubed. So look what happened. Kind of nice the way this worked out. 8x over x squared plus 1 squared. So notice how this time I did some extra work here before moving on to the next step. I got this one fully simplified. Now I can say f prime at x equals 0 when the whole function equals 0, but really that's going to be when the top is 0. Sometimes we're going to show a little bit of work here. Often we've already done the work and we just state the values. You know what I mean? Where would this function not exist? Zach? Not quite on the right track, but it does exist everywhere because to get 0, x squared would have to equal -1, and it can't. If this was -1 plus 1, that would be 0. 0 squared is 0. But x squared can't be -1, not in the real number system, which is what we're working in. So this is where you might just have to be thoughtful and inspect it. In some cases, we'll do the trick where you could do it here. X squared plus 1 less than, equals 0. Like, you could do that. X squared equals -1. X equals the square root of -1. No, not going to work, right? You could do that, but you can also just recognize that f prime at x exists for all x. And again, that has to be stated. So all I have is one value, 0. It's in the interval. The interval was from -2 to 4. So now I'm going to go ahead and find those values. F at 0, f at -2, and f at 4. You could do them in order of smallest. You don't have to do them in order where the derivative ones come first or whatever. You can do them in order from smallest to largest if you like. F at 0 is 0. F at -2 is 16 over 5, which we probably want as well as a decimal for comparison. And f at 4 is 64 over 17, which is approximately 3.8. Therefore, max is 64 over 17, when x equals 4, and the min is 0 when x equals 0. Any questions about that? So far, we're going to do our sketch. Goes from -2 to 4. At -2, I'm at 3.2. So I'm going to mark that, let's say, here. I go down to 0 and then up to 3.8. Questions? We're going to do one more. Okay, so that's the first line derivative. I'm going to show you another way that you can simplify these. Some people like this way, some people don't. If you don't, some people are going to be like, I don't even know what you did. It's fine, do it the other way that we've been doing it all along. Some people just see it like this, and you might like it better. I don't know. It's maybe, well, they're both kind of two steps, I guess, but it just depends on how you see it. So when you have a negative exponent, you can factor it out. And I can also factor out a 5 from the numerators and the 3 from the denominator. So I'm going to get 5 over 3 x to the -1/3. So I'm factoring out that whole negative exponent. When you factor, you're dividing that out of the different parts. So when I divide it out of this first part, x to the 2/3 divided by x to the -1/3 is 2/3 minus -1/3. What's that? 2/3 plus 1/3, which is 1. And often that's kind of what happens, either because the question's set up that way or whatever, right? And I factored out the whole 5/3. So I get x, and I factored out the whole x to the -1/3. Whoops. Sorry about that. So that part's gone, and I factored out the 3 on the bottom, but I've got the 20 divided by 5 is -4. And then I can just write this as 5x minus 4 over 3 cube root x. This is a common way that some teachers, professors, whatever, do it every time. So it's good to have at least seen it, and otherwise you'd be like, what just happened there? Like, it's, if you've never seen it, it's harder to follow. It's a common way of doing it. But how are we doing it before? So I'm going back to that first line. We do common denominator, so I have to rewrite 5. I'm going to write this way, actually. I'm going to leave this one like this for now. Over 3 minus 20 over 3 cube root x, or x to the 1/3. So I already have 3 in both denominators, so I have to multiply this by x to the 1/3 over x to the 1/3, right? And if I want, I can common factor out the 5 at the same time. X to the 2/3 times x to the 1/3 is x again, minus 4, and I end up in the same place. I would imagine maybe a lot of us would have taken 2 steps to get here, though, so maybe this is a bit faster. But anyway, accuracy is more important than speed at this point, I think. Efficiency is absolutely important, obviously, but any questions? Okay, so now we've got the derivative. We've got it fully simplified in the form that we want, and we can say f prime at x equals 0 when? When x equals 4. So like I say, sometimes we don't really show all the work, we just state it. And f prime at x does not exist at 0. So this is the first question we had that's like this. It actually has a value where it doesn't exist. Remember when we talked about this before? Often this happens when you have an asymptote. And but in this process, we probably won't see that because, as I already said, if you have a vertical asymptote, that kind of mucks up the process of maximum and minimum values. But this function does not have an asymptote. The function doesn't. So there's something weird happening in the derivative that it has a vertical asymptote because it has a denominator of 0, but the original function does not. So that's something else. And if you think about it, you actually can figure out what that is from when we talked about continuity and limits existing and that kind of thing and the kinds of places where that occurs. But we're going to go over it together. So let's figure out all these parts. We're going to find f at 4. We're going to find f at 0. That was the only place where the derivative was 0. F at 0 was the only place where the derivative doesn't exist. And then the end points are -2 and 6. And both of those are in my intervals, so I want them both. I'm not ignoring that. I just already have thought of that. F at 4 works out to about negative. This one you probably can't get an exact value of, so you're going to round. If it's fraction, keep it as a fraction, right? But with the square roots and cube roots and all that stuff, these ones don't work out nicely. F at 0 is 0. F at -2 is approximately -19.0. And F at 6 is approximately -13.2, I think. Hopefully those are right. And for the last time, remember, that's the original function. You're not plugging back into the derivative. So therefore, the max is 0 because all the other values are negative when x equals 0. And the min is approximately -19.0 when x equals -2. From -2 to 6. Is everybody okay? Everybody ready? We're starting at -19, approximately. It's the minimum, so we're obviously going up from there. And again, you got to plan this stuff out to make sure you draw that low enough that you can do the rest of the graph. What do you think is happening at the maximum of 0? That's right. We call it a cusp. So we talked about these before. It's cusp, but that's where it's a cusp. How do I know? Because it's not an asymptote. Where else would the derivative not exist? At a break, it's not a break. These are continuous functions on the interval. So it's not a break. It's not a hole. We would have recognized it as a hole. It's not a vertical asymptote. The only other place where the derivative or where the limit doesn't exist, as we talked about in the past, is at a cusp. What does a cusp look like? It looks like this. Okay. Then I have a turning point at 4, because that's where the derivative was 0, a horizontal tangent line. And it goes up from there, because at 4, it's at negative 15.1, but then it goes back up to negative 13.2. So this is, so see how you really got to think this through and make sure you get all the pieces. 13.2, this is negative 15.1, this is 0, and I want these points labeled as well. And there you have it. So in this case, I know that this is a turning point because it's got a horizontal tangent line and it goes back up from there to negative 13.2. That's the only way I know that happened. Otherwise, you wouldn't know if it's a turning point or a cubic twist horizontal tangent line like that. Seema.
Does it matter what side you label?
What do you mean? Like if I put the negative 19 here?
Like on the other side?
Like put these there?
No, like put the negative 15.1 like on the other line.
Oh, no, I guess not. I mean, it's sort of closer to that side, so I labeled it on that side, but yeah, I see what you mean. Yeah, no. I wouldn't put that one on the other side. That would be a bit weird, but otherwise, sure. As long as it's clear, make sure it's clear. Any questions? Other questions? So the practice that you're doing today, the first question is really easy. It literally gives you 4 pictures. You just look at it and say, where's the maximum in? Question number 2 is easier ones. So we're only assigning C and E. Okay. So we're doing number 1. I think it froze it. Number 1, 2, C, and E. And then all of number 3. Number 3 are more complex ones. If you want more simple ones to practice, all the other ones in question 2 are fine. They're just easier. They're all kind of polynomials, I think. So maybe not really worth doing a whole bunch like that. Question number 3 are the ones that get a bit more interesting.